Okay, perfect. So last time we were looking at the following proposition, and we actually proved half of it. So let me recall what it was. So we looked at a triple M omega mu, a Hamiltonian G space. And then, well, there were two statements. First of all, if X in the dual of the Lie algebra G is a regular value. So this is the same as for all M in the fiber, the stabilizers are finite. And I think, so this part we proved. Now for the second part, we assume that X in G star is a regular value. So then we have the following. We can denote by I the embedding back to M of the fiber. Now fiber is a submanifold. And then the statement was that the kernel of the restriction of the symplectic form omega to some point in the fiber, so here M is a point of the fiber, is exactly equal to the tangent space of the orbit of the coadjoint stabilizer Gx passing through M. So this is the coadjoint stabilizer. That is G and G. So maybe before proving it, let me make one small remark. Perhaps we'll get back to it later on, or let me state it as a fact. So assume that G is a compact connected Lie group. Then all coadjoint stabilizers are connected Lie subgroups. So maybe we come back to discussing this fact in a little bit more detail later on, but just maybe at the moment this is good to know. All right, so let's finish the proof. So the first part we've done last time. So let's finish the proof of the second part. Right. So first, let me recall from the previous time what we had. So let's consider the tangent space to the fiber at some point M. More or less by definition, right? So this tangent space to the fiber coincides with the kernel of the push-forward map, right? So you have a map mu, which maps your manifold M to G star. So you want to fix the point in the image. So what are the tangent vectors which are tangent to the fiber? These are the tangent vectors which don't move the point in the image, right? And the points which don't, the vectors which don't move the point in the image, these are vectors which are killed by your push-forward map. Right? And we saw by a previous proposition that what is this? This is exactly the omega orthogonal of the tangent space to the G orbit. So note that here we have some new gadget, right? So this is the GX orbit. But this is just the normal G orbit. So there is a G orbit passing through the point M. It has a tangent space. And its omega orthogonal is exactly this thing. Now, yeah, I don't know why do I always need to look at those nodes. That's probably because it's kind of somewhat tricky. So now we want to discuss what is this. What's the kernel of this form, right? So we have a symplectic space. So the tangent space to the whole manifold is a symplectic space. And in this symplectic space, we consider this subspace. We restrict the form to the subspace. And we want to know what's the kernel of the form. Now let me write down something, and then you tell me whether it's obvious or not. So I think we should take the subspace and intersect it with its omega orthogonal. So this is a kind of general statement. Whatever is the omega a symplectic vector space, I consider U inside V. And if I want to know what's the kernel of omega restricted to U, it will be U intersection with U omega orthogonal, right? That's more or less the definition of U orthogonal. Right. Right. So this is kind of obvious. Now let me use this previous proposition, right? I actually know what is this tangent space, and it turns out to be already omega orthogonal of something. So this is the omega orthogonal to the orbit, intersection with the omega orthogonal of this omega orthogonal. But of course, if you take the omega orthogonal twice, what happens? You simply get both omega orthogonals removed, right? So this is an intersection of OM, omega orthogonal, simply with the tangent space to the orbit. All right. Now let me rewrite it again in the following somewhat. So now I replace again this gadget with this gadget. So that's the intersection of the tangent space to the fiber with the tangent space to the orbit. Now, since these are both nice submanifolds, let me somewhat bravely rewrite it in the following way. So that's the tangent space of the fiber intersection with the orbit. Now, what's the intersection of the fiber with the orbit? Right? So you want to be on the orbit, but you also want to be in the fiber. But this is more or less tautologically this thing, because what is Gx? So Gx is a subgroup which moves you in the orbit, since it's a subgroup of G, and which doesn't change the point in the cotangent, in G star under the coadjoint action. And now, since the moment map is equivariant, right? If you want to stay at that point, you have to use this subgroup. So. I think here we're using the equivariance of mu. Okay. So that's it for the proof. In fact, my plan now is to state and prove the symplectic reduction or Marsden-Weinstein's theorem. But before doing that, let me still do a little bit of preliminaries, or like recall you some small things about group actions. You probably know all that, but let me just briefly state it. So what we will need in this symplectic reduction theorem is free group actions. So action of G on M is free. This means that for all points of M, the stabilizers are trivial. Assuming this is the case, we also have, for any, let's choose some point M in M, and let's consider the orbit of M inside capital M. And then this orbit is diffeomorphic to the group G itself. So that's because, or we can organize a map from G to OM, which is simply given by this formula. So we know that this is a smooth map because the action is smooth, and we know that this is a bijection because there is no stabilizer. Right. Now let's put ourselves in this situation, and let's do the tubular or equivariant tubular neighborhood theorem in this case. Right? So what does tubular neighborhood theorem tell us? So we want to look at the at some neighborhood of the orbit, right? So we say that our orbit is contained in some neighborhood sitting inside of M, and now we're going to build a model of this neighborhood. So what's going to be this model? We know that the model will be, or M sitting inside V, right? Inside the normal bundle to the orbit. Now for the normal bundle to the orbit, we also worked out what normal bundles to orbits are. And let me recall you, so this is a product, some kind of tricky product of G over Gm times the vector space, which is a normal fiber of the normal bundle at a point M. So in principle, this is a relatively tricky object. Remember, we looked at it last time, but not this time. Right? Because Gm, what is it? Gm is simply a trivial group. So in this case, it is actually equal to G cross an M or M. So this is our group. This is just a vector space. Right? So here there is this V sitting inside G cross the vector space. And this basically means that V, so V will be isomorphic to G times some V prime. And V prime is some kind of open neighborhood of the origin in this vector space. Right? Now, what's the G action in this model? So G is mapping a pair, say H and a vector V. So what is this G action? Yeah, so it acts, I think I probably chose it, if I write it in that way, this means that it just acts on the left, right? So this is just by left translations on G. So it maps to GH. So in fact, this vector space, in this particular situation, is simply a spectator, right? Nothing happens. You have a group G, it acts on itself by left translations, and this vector space is doing nothing. So in particular, this implies the following. Let's consider the quotient space M mod G, right? So this is M modulo the equivalence relation So in principle, usually this is, in differential geometry, this is a dangerous construction because quite often a quotient space may not be manifold, may be very singular, may have various pathologies. But again, not this time. Because, so now let me claim that this quotient space is a manifold, and that's because we just built charts for this manifold, right? So in our local model near the orbit, we can take a quotient. And this quotient is going to just kill the first thing. So locally, we have V mod G, which is G cross V prime mod G. And this is simply equal to V prime. So this V prime is a chart on M mod G. So locally near this orbit, so our space just looks as a neighborhood of origin in some vector space. That's what we want. Now, moreover, I'm not quite sure. I think you recently had an informal seminar on characteristic classes, right? So this probably means you know what principal bundles are, right? Or not. So let me still so M is a principal G bundle. Meaning what? Meaning, okay, let's simplify things. So M carries a free G action. G action. And M mod G, let me call it B, is a manifold. And this manifold has an atlas, let's say UI, such that, let me denote the projection from M to B by pi, such that the preimage of each chart is isomorphic to G times UI. Right? So we cover our base with charts, and over each chart you just have a direct product of G and UI. So that's more or less a definition of a principal bundle. Not quite, but and that's exactly what we see here, right? So we've just, again, with this 2B neighborhood theorem, we just constructed those trivializations. We not only constructed the charts, but we constructed trivializations over these charts. So our M near the orbit looks exactly like G cross V prime. V prime is our chart. This should be the place of UI, and that's exactly what we have. Right. Now, maybe one more thing to remind you. Again, I'm not quite sure. Maybe this was, even part of the introductory lectures on differential forms. But you tell me if not. So did you have a notion of basic forms? All right, so let me recall the setup. So we have P to be a principal G bundle. So we have a free G action on P, and we have those local trivializations over the charts in B. So let me denote this projection by pi. So then there is a pi star map which maps forms on B to the forms on P. Now we would like to characterize the image. Right? So this pi star map has the image, so the forms on B map there. In fact, this is, it turns out to be an injection, so there is no kernel. But the question is, what's the image? And the claim is that the image consists of so-called basic forms, which are defined in the following way. So this is the intersection for all psi in G of the kernel of Alekseev M intersection with the kernel of L psi M, psi P. Where these are fundamental vector fields. Right. So first of all, how is it? How familiar are you with this statement? Not really, right? All right, so let me do the following. Maybe I don't really prove it, but at least I explain in a hopefully somewhat convincing manner why this is true. So first of all, it is relatively easy to see that the image of pi star is contained in omega p basic. So why is it true? Right, so here is our base, and over this base we have the principal bundle. So the preimage of a point is the orbit of a free action. So roughly speaking, it's a copy of our group G. Right? Now, so suppose we've chosen here a point, let's say P, and it projects to a point B in the base by the, so from here to there acts the projection. So we have P in P, and then 5P is B in B. Over here there is a tangent space to the fiber, the tangent space to the orbit, and it is spanned by the values of fundamental vector fields. Right? So here, for instance, we have tangent space to the orbit through P. So that's the image of the map from G to CP of P. And it consists of the values of fundamental vector fields. It's what I'm saying now, right? I'm saying it in many ways, but it's more or less tautology, right? It's roughly tautological. Right. Now the question is, what happens with all these vector fields when I project them with the corresponding push-forward map, with the corresponding tangent map to the tangent space on the base? So what happens to them? Sorry? Yeah. So they're going to all vanish, right? Because how is it? I have the fibers over this base. So, and these guys are tangent vectors to the fibers. Maybe my drawing is misleading, right? So, okay, I take it back. So that's the tangent space to the fiber, and then inside there are those psi p's, right? They're not allowed to look the other directions. So it maps CPOP to 0, more or less by definition, right? So because you kill the fiber, so all these vectors are killed. Now, so what are we claiming here? We take some form, let's say alpha, on the base, and we take a pullback of this form which is a form on the total space. And now we are asking a question: what will be Yodex IP pi star alpha? Well, say if you want to evaluate it at the point P, you know, you can always like play with those pull back and push forward. So basically all the definitions of pullbacks and push forwards are such that I can now bring this computation back to the point B and say that this is iota pi star psi P alpha, and then pull back, and then pull it back again, right? So I can do always the computation either upstairs or downstairs. But now downstairs, all these guys, they simply vanish. So whatever alpha is, so this is always 0. And it will be similar for the Lie derivatives. So let me explain it in words. So what is a Lie derivative? So right, you look at the flow of the exponential of your vector field, right? So and you start moving your differential form with this flow, and then you differentiate at the point whatever t equals 0, right? That's the definition of the Lie derivative. So that's what happens upstairs. Now you bring it downstairs. What happens with the flow when you try to project it? Right? You have a flow which moves you in the fiber. Of course, flows don't need to project under projections. But now this flow will easily project. So you have some flow in the fiber. What is the image flow under projection? Identity, right? It's a trivial flow. It doesn't flow anywhere. Now, what's the Lie derivative with respect to this identity flow? It's 0. The vector field is 0, Lie derivative is 0. So nothing happens at the base. So from this perspective, if you pull back something from the base, it's kind of trivially seen that nothing happens to those pullbacks under those operations in the fiber. So this conclusion is more or less obvious. Now let me just perhaps I don't think I want to prove the opposite embedding, but let me still comment on it a little bit. So y image of pi star is equal to omega p basic. So in other words, what happens, so you have a basic form. So you have an element, let's say beta, inside this intersection of kernels. And you want to show that actually it's a pullback of something. Right? Now, let's look at the situation locally. So we know that our P is a principal bundle. So this means that locally P is equal to G times some chart U on the base. Now to simplify things, let's assume that this G is not a general compact connected Lie group. Let me say for example, that G is just a torus, TK. So it's a torus with coordinates theta 1, theta k. And let's say here we have coordinates on the base x1, xn. Right? Now, how do these differential forms, how does the differential form beta looks like? Well, I will introduce two multi-indices. Let me call them I and j, and let me write it in the following way. So this is a sum of betas of x theta. So x and theta here stand for all the coordinates x and all the coordinates theta. So dxi wedge d theta j, where these are multi-indices, and you know what this notation is. All right, so that's just the most general situation that we have. And now we know that beta is in the intersection of those kernels, right? Now, how do the fundamental vector fields look like? Now, G is isomorphic to Rk. And for instance, here we can take the element psi I, which is 0, 0, 0, 1 at the ith position, and zeros in all the other positions. So that's just a basic vector with 1 in the ith position. So now concretely, what is this psi I on this G, on this TK times U? So what is this vector field? So, right, this is d over d theta I, right? We know that the action of a torus on itself by translations, so the corresponding vector field is just this guy. So, first of all, we know that beta belongs to the intersection of the kernels of all contractions with this vector field. So, all contractions with all d over d theta I, they give 0. What does it tell us? So we know that beta belongs to the intersection over I from 1 to k, kernel iota d over d theta I. So then what? So what does it tell us about this differential form?
The d theta part is 0.
D theta part, so this multi-index is actually 0. So you cannot allow any d thetas, because then so the contraction won't be 0 for at least some of them, right? So this implies that this guy is actually not there. So j is equal to 0. Well, very well. Now, we also know that beta is in the intersection of kernels of Lie derivatives d over d theta I. So how does the Lie derivative L d over d theta I act on beta? What does it do? Very concretely in this formula. So if I apply it to this guy, what will happen?
We'll give derivatives with respect to theta over beta.
Right. So the L d over d theta I doesn't touch these guys. It simply takes a derivative under theta of these functions. Yeah, I should say beta ij. So will be derivatives of these functions. Now we know that all of them vanish. Well, so this means the functions do not depend on theta. So beta ij x theta is actually beta ij of x. So this means beta is equal to sum over I beta I, now we can forget j because j was 0 anyways, dxi. And this is of x. So this is actually a pullback of the same form. So like these expressions are identically the same, but now I think of it as a form on the base. You should see that it actually glues, but it is more or less obvious. So I think maybe we don't finish the argument, but in essence, we see that it's a pullback of something. Right. So let me finish this hour by stating a big theorem, and then next hour we start with comments and then with a proof. In fact, with all we've done, the theorem is actually an easy theorem. Is it okay if I erase this part to take the right. Okay, so we start as usual with gm omega mu. A Hamiltonian G space. So we choose x in G star. A regular value. And this gives us the following diagram. So we have a fiber over x. It's embedded back to M. And we denote the embedding Ix. And now we know that there is a G action here. And we assume that this Gx action on the fiber is free. So if Gx action on the fiber is free, we know that this is a principal Gx bundle. And there is a smooth base. Let's call it Mx. Which is a quotient of mu minus 1 of x by gx. So we denote this projection by pi x. So then Mx is symplectic. With symplectic 2 form such that Ix iota star omega is equal to I star omega x. I think probably I should say symplectic with the unique symplectic form omega x, which satisfies this equation. So we're going to discuss this statement in more detail after the break, but maybe already now I can say this is a relatively simple statement of kind of the proof, not going to be difficult, but it had an enormous influence on the kind of, it has like an infinite or whatever, kind of huge countable, whatever, infinite number of applications. It doesn't look like that at first, but turns out to be the case. So let's have a break, and we'll have comments and proof after the break. So let's do the proof. I'll start with an observation that perhaps we should have made before, but we didn't do it. We have our Hamiltonian G-space. Omega is a 2-form on M. And it turns out that this form is automatically G-invariant. So just to recall, why is it like that? Since G is connected, it's enough to show that the Lie derivatives of fundamental vector fields kill omega. So then this implies the G invariance. So, and if we compute the Lie derivative, so we know that as usual, we use the Cartan's magic formula. And in the Cartan's magic formula, we have now two parts. In this part, we get 0 because omega is closed. Maybe I still rewrite it. So iota psi m d omega. And this is 0 because omega is closed. And then by the moment map equation, this part is d of d mu psi. And this is 0 because the theorem differential is a differential. So, and this is also 0. So everything is equal to 0. So omega is automatically G invariant. Now let's just make an observation. So we have I star x omega, and this is a 2-form on the fiber. And since omega is G invariant, what can we say about the invariance of this guy? Is it invariant under something? So it is Gx invariant. Is it obvious? Is it not obvious? I think it is obvious if I state it in the following way. Omega is G invariant. This means that omega is also Gx invariant because Gx is a subgroup. Now, the embedding of the fiber into M is a Gx equivariant map. So, an invariant object pullbacked by an equivariant map is an invariant object because action commutes with pullback. So if I state the arguments like that, I think it is obvious, but at least it needs a little bit of thinking. Okay. So in particular, this implies I star x omega is in the kernel of xi, let's call it xi mu minus 1 of x, for all xi in Gx. Right? All the fundamental vector fields that we extract from the Gx action, and here we should put the Lie derivative. Right? So, yeah, sorry. So all the Lie derivatives of fundamental vector fields which come from Gx, they kill this guy. Now, what about the contractions? So recall that in the previous proposition, which looked somewhat technical, we computed this kernel, right? And the kernel was equal to what? Exactly to the tangent space to the orbit. Now, what does it mean if we translate from this somewhat abstract language? So this means that if we take an element psi in Gx, so then the value of the corresponding fundamental vector field will be, of course, in the tangent space to the orbit. And this statement tells us that iota of this psi mu minus 1 of x applied to I x star omega will be 0, right? Because that's exactly the kernel of omega. So it's actually in the intersection of the kernels of contraction maps. So this part is kind of obvious, but for this part, we worked with all those technical lemmas. And together, they are telling us a very simple thing, that this restriction of the two-form is a basic two-form on the fiber. But now we know if it is basic, it's a pullback of something, right? So there is a unique omega x in omega 2 of the base such that the beautiful formula that we had in the theorem holds true. So this defines for us omega x. So by the way, did we prove the theorem?
Like, without the kernel?
Yeah, but I think we're not far from proving the theorem, but now we should show that this is a symplectic form, right? So we know that if you restrict this symplectic form to the fiber, then it's basic. Now remains to show that omega x is symplectic. Now an easy question for you, why omega x is closed? Right? We need to show that it's closed and non-degenerate. So why is it closed? So what happens if we take d of this equation, right? So what is d of the left-hand side? 0. So we get, right, 0 is equal to d of the left-hand side. So this is, of course, equal to d of the right-hand side. And here we can always exchange d and a pullback. So we know that pi star x of d omega x is 0. Now we want to conclude that d omega x is 0. And for that, we need to say that this guy is injective, right? So this guy is an injection. And that's why this implies d omega x is 0. So now omega x is non-degenerate. So why is that? So is it obvious? Is it non-obvious?
So you know the kernel of ix omega starts if they know the kernel of ix omega.
Yeah, so we do know the kernel of this guy. So I think, is it like, let me state it in the following way. So suppose we have the point M in the fiber, and then we have pi of M. I actually was long hesitant. How should we denote it? N? Or, yeah, I don't know a good notation. So let's say N, the point of the base. And suppose we have a vector in the tangent space on the base, which is in the kernel, of omega x. Then I think the preimage of this vector, so all the preimage of this vector in the so to here there is a projection map from the tangent space of the fiber, and I think all the preimage of this guy, it has to be in the kernel of I star omega x. Is it correct? So here contain the preimage. So pi x star minus 1 of v. I think it should be in the kernel Is it true? I think it's actually true, because so you have omega x star uv equal to pi x star omega x of uv for any two lifts, right? So that's again kind of this push forward, pull back for if pi star u is small u, pi star v is small v. Right? So you have pull back, push forward, so you can do computations upstairs or downstairs. Right? So I take computation downstairs. U was in a kernel, which means that for arbitrary v, this was 0. Now I take any preimage of u, and then I take arbitrary v, because a preimage of an arbitrary vector is an arbitrary vector. So it is in the kernel of this form. But we know that the kernel of this form is the tangent space to the gx orbit. So this means that all these vectors, they're in the tangent space to the gx orbit. But then, what was the vector on the base? If upstairs it's tangent to the orbit. That we discussed recently with my picture, which perhaps was not completely adequate. Right? So what's the 0, yeah. Of course, if this is the case, this means that v is equal to 0. So this argument is somewhat more tricky, and that I think that's for this argument that we were working with those two technical propositions, because we do want to establish that. That's, let's say, so the fact that you do get a two form downstairs, this is a kind of a little bit soft fact. It's nice, but I think what really makes it beautiful and exciting and efficient, and why like everybody wants to use it, that's because there is this non-degeneracy. So and kind of maybe the non-obvious part of it, so you take your two form and you restrict it to the fiber, and then you do get a kernel, right? That in the intermediate step, the two form on the fiber, it is closed, but it's not at all symplectic. It has a huge kernel. But now you descend to the quotient, and there all of a sudden kind of this bad property disappears again. So you have no kernel. So you get again a symplectic structure. So I think that's this kind of, you cannot make it work without this intermediate step, more or less, because right, you want to define it with this, so it's associated to the fiber, and the intermediate step, it has some strange object, or object which has less good properties. And then you can again kill all the bad properties and get back the symplectic structure on the quotient. I think that's a kind of non-trivial part of it. So I would like to spend the rest of the hour by doing some kind of fun stuff, hopefully. What I need one small proposition and one fact, which we actually give you as an exercise in the next problem set. And otherwise, it hopefully will be some interesting geometry. So one small proposition which says the following. Suppose you have M1 omega 1 mu 1 and M2 omega 2 mu 2, two two Hamiltonian G spaces. So then what you can do, you can take the direct product of M1 and M2 with G, the diagonal action. You can add the two forms. Here, well, is it okay if we use, so this notation is not completely correct, right? I want a two form on M1 cross M2. So strictly speaking, I should define projection from M1 cross M2 to M1, projection from M1 cross M2 to M2, and take the pullback of the forms back to the product. But I just write omega 1 plus omega 2. And mu defined as a sum of moment maps. And we claim that this is a Hamiltonian G space. Well, why is it the case? Well, it's clear that omega 1 plus omega 2 is symplectic. That's because the sum of two closed forms is closed. And now we have a sum of two non-degenerate forms which are on the direct sum of two vector spaces, right? So we have T mm is equal to Tm1 m1 plus T m2 m2, and omega, let me write it in this way, is omega 1 plus omega 2, the two form on this one and the two form on that one. So if this guy has no kernel, each of them, then this guy has no kernel. Well, the equivariance is kind of obvious. So this is mu1, G1, right? So everything adds up. And finally, the moment map equation. Right, since the G action is diagonal, the fundamental vector fields will be fundamental vector field on M1 plus fundamental vector field on M2 applied to omega 1 plus omega 2. So each of them chooses its own omega because it's a direct product. And this gives the So you see, like everything works really very, very easily. The two forms add, the moment maps add. And now one fact, which is actually the first exercise for the next in the next problem set. So recall that we have this symplectic manifold, which is a unit sphere in 3 space. So it's symplectic with omega the area form. Now, the first exercise in the problem set for today is to show that if you take rotations around the z-axis, then this is a Hamiltonian S1 space. Right? Now, the exercise for the next time is slightly more complicated. So we take the group of rotations of R3. Rotations of R3 rotate the unit sphere, right? Now, the claim is that this action on S2, together with this two form, again the area form, and the moment map. So the moment map from S2, it should be to the Lie algebra of this SO3. Now, what's the Lie algebra of SO3? In fact, this is a part of the exercise as well. But let's just what's the dimension of this SO3? What's the dimension of the group of rotations of the 3 space? You probably you might know from some elementary geometry course that every rotation is a rotation around some axis, right? So you need to choose an axis, which means a vector on the unit sphere, and then you need to choose the angle. So all in all, what's the dimension of this manifold, SO3? So for the 2 sphere, it's 2, plus the rotation angle is 3, right? So, it must be a map from S2 to the to R3, to the Lie algebra of our rotation group, which must be R3. So now, what's your guess for this map? Right. So we already have this map, right? The 2 sphere is actually embedded, naturally embedded in R3. So this is just the embedding. Hamiltonian.
But then is the identification of the Lie algebra with R3 canonical?
Sorry?
You must choose the basis first, right?
Sure. Yeah, I'm cheating a little bit, but yes, you can always choose it such that it will be. Yeah, sure. Of course, I. Right. Maybe one small remark. Suppose that I choose a positive real number, let me call it R, and I decide that now, instead of taking the standard area form, on the two-sphere, I would like to replace it with r times omega. So the first question kind of say, and I want to write r times omega. I rescale my omega. So is it still a Hamiltonian SO3 space? So remember, like there are three conditions. So the space should be symplectic. Is it? Sure, right? Non-degeneracy, if R is positive, nothing happens to non-degeneracy, nothing happens to closedness of omega. Now, the second requirement was equivariance of the moment map. So the moment map I haven't changed yet, so it is equivariant. Now, what about the moment map condition? So remember, there is this moment map condition, Yodek psi m omega is g mu psi. So I multiplied omega by r. What should I do on the right-hand side? Now I guess the equation no longer holds, right? So what do we do? Yeah, we multiply mu by r. So mu is the embedding times r. And then the statement is still true, right? So trivially. Okay. Now, a fun example. So let's take M to be a product of several copies of the unit sphere. Let's say n copies. Equipped with the symplectic forms, which are the area forms, multiplied by kind of random positive coefficients. Now, this is by the two considerations. So we can multiply Hamiltonian G spaces. We can rescale the symplectic forms and the moment maps. So this is a Hamiltonian SO3 space. So in fact, its moment map does the following. So if I take n points on the unit sphere, what I need to do is the following. I multiply each of these points by the corresponding factor, because I should multiply the embedding. And then I should add them up, because the moment maps Mn supposed to add up. Let's think of how it looks like. So you have your product of unit spheres. So here you have those M1, M2, and so on through Mn. So these are unit vectors. Right? So that's a point of our manifold M. And where is it mapped? So you should take M1 and multiply it by R1. And then you should add to it R2, M2. And so in the end, you will add all those vectors. So those vectors, the direction is decided by the choice of a point on the two sphere. And then the length is decided by the factors that we included, by those positive factors. So, so that's the moment map. Now, what about So what about the reduction? So we want to consider the space M0. So mu minus 1 of 0 divided by the stabilizer, G0. So what's a coadjoint stabilizer of 0? You have a vector space, you have an action by linear transformations, you have the origin. So who fixes the origin? Everything, that's right. Which is G, which is SO3. So of course, the first question is when 0 is a regular value, right? Because our theorem, I recall, it works for regular values. Right. So this is, or maybe better say, when the stabilizer GM is trivial. So this is a stronger statement for all M in mu minus 1 of 0. Okay, so let's compute the stabilizer. So what's the stabilizer of a point? So our manifold is a product of manifolds, in this case a product of spheres, and our action is a diagonal action. If we want a stabilizer of product of points, so each of the points should be stabilized, right? So this is simply the intersection of stabilizer groups for each of the points. Now, what's the stabilizer subgroup for a unit vector under rotations?
Rotation around the
Yeah, so these are rotations around that vector. So now you have your n unit vectors. For each of them, the stabilizer is rotations around that vector. Now, what's the intersection?
zero unless one point at the single.
Right, so it's either trivial or it is G, say M1 if Mi are equal to plus minus M1 for all I, right? So that's so then there will be a circle subgroup which stabilizes everybody. Now, so and trivial otherwise. In fact, that's what we want. That's what we don't want. Now, when does this happen? Well, let me tell you when does this happen. So this means that all these vectors, right, they are now collinear to each other, and they add up to 0. So this means that sum of Ri epsilon I from 1 to n is 0 for some epsilon I which are plus or minus 1. Right? You should have some linear combination with coefficients plus or minus 1 of Ri's, which gives you 0. If that's the case, then you can find a point in the fiber of 0 which has a non-trivial stabilizer. And then the action is not free. But otherwise, it is free. So that's good because this is a criterion which only depends on the choice of Ri's. So if you choose your Ri's wisely, such that such a thing will never happen. And of course, you can always choose such Ri's because imagine the space Rn where Ri's live. So this is a finite number of hyperplanes. So you need to take a complement to this finite number of hyperplanes, and whatever else you choose in the positive quadrant for Ris is your friend, right? So let's assume Ris are such that 0 at Gm is trivial for all m in the fiber of 0. Well, then m0 mu minus 1 of 0 over SO3 is a symplectic manifold. So what's the picture for this symplectic manifold? So we can think of our points as unit vectors, but we can also think, if we want, of our points as vectors of lengths R1, R2, and so on. So we have a number of those vectors, so the lengths of the vectors are fixed, and now we have to come to 0 in the end. So, so this is actually an element of the fiber, right? So the element of mu minus 1 of 0 is a collection of vectors of given lengths such that their sum is equal to 0. So it's a kind of polygon in this free space. Now, remember that we have to divide it by SO3. So we can actually, around this point, we can rotate the whole configuration. So it's a moduli space of polygons in R3. So polygons with given lengths, modular rotations. So these are called polygon spaces. And sometimes one uses the following notation, right? This M0, it depends on the lengths. Its symplectic form depends on the lengths. So we get a huge collection. So you can choose those. You can choose n. You can choose these numbers. So it's a kind of huge collection of relatively complicated symplectic spaces that we produced, you see, out of nothing. Like kind of this theorem. It's an example of the power of the Marsden-Weierstein's theorem, right? It was all kind of very routine, very easy, like kind of some tangent space equal to this or that orbit. Now, wow, we just take some elementary geometric construction and it produced from it the whole world. So there are recent papers, or recent, like maybe 10, 20 years ago, about the topology of those polygon spaces. So this is a research subject, polygon spaces. Maybe just the last remark before we conclude the session. So let's compute the dimension of this M0. The dimension of the sphere times n. So 2 is the dimension of S2. Now we take the fiber. So we take a fiber of a regular value. So what will be the dimension of the fiber? So this is the dimension of M. So the dimension of the fiber, right, for a regular value, that's dimension of the source minus the dimension of the target, right? So the dimension of the target is 3. So minus 3. So that's the dimension of mu minus 1 of 0. And now we divide by a free action of SO3. SO3 is three-dimensional. So the dimension of the base is the dimension of the total space minus the dimension of your group. So we get 2n minus 6, which is 2 times n minus 3. In particular, we see that if n is equal to 3, then the dimension of M0 is equal to 0. And this is easy to imagine. What happens here? So we're given 3 numbers, R1, R2, and R3. And we're asked to build a polygon, which means a triangle. Right? So this will be a triangle, modular rotations. But then modular rotations, a triangle is unique, if it exists. Of course, if R1 and R2 verify the triangle inequalities. If not, you get an empty set. So if it is non-empty, it's unique. Now, the first interesting case is n equal to 4. So then the dimension of M0 is equal to 2. And in fact, that's one of the problems in the problem set to figure out what it is, this polygon space. So this will be quadrilaterals. Modular rotation. So you have 4 vectors of given lengths. Their sum is equal to 0. You are allowed to rotate them as you want. And so the question, what it is already like as a manifold. So it has to have dimension 2, right? So what is its symplectic form? What's the volume of this symplectic form? So, right, you see, you get kind of, up to now, I think maybe it was not very good because we suffered a little bit of the lack of examples. I was giving you all those technical propositions, but there was no things with which we can work. Now, as I say, you can start here with polygon spaces and do your research there if you want. Maybe one small thing. So in the next problem set, there are some problems that I already explained a little bit, and there are some problems about coadjoint orbits. Unfortunately, coadjoint orbits didn't fit in this lecture, so they will be in the next lecture. But, well, if you want, you can look at those problems. If not, next time we'll see coadjoint orbits, and then we'll discuss coadjoint orbits also at the exercises. All right, so that's it for today.